Okay, Physics 15 class, so we're continuing. This is chapter 13, electric circuits in the book. Okay, chapter 13, electric circuits. Where am I? I'm on page approximately 266 right now. We're looking at a picture of a battery, and there's wires going to a light bulb. We got a little equation there, so let's talk about that. So last time, chapter 12, we talked about static electricity. Static electricity was, you had a balloon. If you rub a balloon, right, you can stick the balloon to the wall, like in the wintertime when it's dry, or stick it to your hair. You can rub the balloon on your head, right? And we talked about that. That's electrons. Some substances, either there's more electrons that have gotten onto that balloon or your hair, makes it negatively charged. Other substances will become positively charged if the electrons are rubbed off. Either way, the thing will have a charge. It's all about electrons. We all know what electrons are. When you have an atom, there's a proton, and there's electrons right in outer shells. Or some substances like metals, copper, silver, wires, electric wires. In those things, electrons can flow. So that's different. Static electricity, that's a buildup of electrons like on your balloon or on your hair, or in a cloud. Electrons can build, but then it can discharge, right? Lightning is when it discharges, so there's a flow of electrons. So now we're going to be talking about the flow of electrons. So that's electricity. We all know, we've all heard of electricity, right? Electricity flows in our house. We have we drive a car, we've been in a car, there's lights, we have a flashlight, your phone has a light in it. How does that work? So here is a little diagram, right? You buy a battery will be 1.5 volts, it depends on the batteries. There's all kinds of batteries for your phones and different things. But you buy a flashlight battery, a lot of them are 1.5 volts, right? If you have a wire going from the positive end, right, batteries will have like a little plus and a little minus. And so they're showing the flow of the current. Just some trivia. Electrons actually flow from the negative to the plus. That's what happens. That's the direction the electrons are actually flowing. When Benjamin Franklin, way back when because he's the one that came up with positive and positive and negative. Well, he took a guess, because at that time he was just discovering it. So he guessed wrong, but it doesn't matter. So we think of positive flowing in this direction, that's okay. But just keep in the back of your mind, the electrons themselves, the tiny little electrons, they physically are going from the negative terminals through the light bulb and into the positive, right? But we think of, when we think of electricity, we think of positive to negative. We can think of positive going this way. That's okay. That's a lack of electrons. It actually works the same way, but don't let that confuse you, okay? I'm just telling you the facts. So what happens is, so we learned about charge last time. It's a coulomb, right? We're not going to worry too much about that. But the charges are measured in this thing called the coulomb, and that's fine, right? But it's electrons. So if you have a battery and you have wires and you attach it to a bulb, or if this is a flashlight, say, and you flip the switch, that's the same as if I connected a wire to this flashlight using a rubber band. Electrons are now flowing, and they're physically flowing through the wire, right? They're going through the little element, right? On an old-fashioned light bulb, there's a little heating element. The diodes work slightly different. Most of the modern ones in your phone are diodes. But an older flashlight, there's a little heating. Electrons are going through that. That has a resistance. What it means by resistance, it's a little bit harder for the electrons to go through there. They heat up the little element. They actually heat it up. It gets hot and it emits light. And it's a little bit tougher for the electrons to go through that. It's called a resistance. So there's three parts to an electric circuit. There's the current, which is I, right? There's the voltage. We know that a battery, you got to get the battery that has the right voltage for your device, right? Voltage is the power source. That's what you need, a voltage, and that's what's going to enable the electrons, give it the energy, the power to flow through, right? Then your wires, where the electrons flow through, there's always a resistance. There's always some kind of resistance. Bigger, thicker wires have less resistance than thinner wires. Here in a light bulb, it's a tiny little thin wire, so it heats up. So resistances come in different values. It's in ohms, right? Well, you'll get more used to that later. Current is in amps. You might have heard of 100 amps, right? And in voltage, we've all heard the word voltage, okay? Amperage, amps, that's how much current is going through. So here we have a simple little equation. If we wanted to say, well, if we have a battery that supplies 1.5 volts, and here's a little light bulb, and it has 20 ohms of resistance. Resistance is it's tougher for the electrons to go through, for the current. I'm going to say current from now on, to current to flow. And current flow, like I said, even though the electrons are going this way, we say that current flows from positive to this way. And that's okay. Just keep that in mind. It's because Benjamin Franklin didn't know, right? He was a genius, but he was just discovering all this, right? So we say the current flows this way, that the positive charges go that way, okay? So the current, so if you have 1.5 volts divided by 20 ohms, that's going to give you 75, now milliamps, of course, so it would be 0.075 amps, right? So let's look at this in a little more. Let me go the other way. Okay. So Felix, you have such high-tech writing configurations. Where do you get your supplies? Well, I get it from the Rice Krispies company. Trader Joe's. Okay. Always recycle, right? Okay. So, let me just write this so you can see it. So if you want to measure the current, like say in a battery circuit, it would be the voltage divided by the resistance, okay? Now current is going to be in amps. This is in amps, okay, that's the unit. Resistance is in ohms. Ohms, there's this little symbol, all right? You can write that or just write the words OHM for ohm. And then voltage, well, voltage is in the unit is volts, right? So you divide, and then of course it goes the other way. If you have voltage, okay? So you can see that my hand's in the way, so I'll move my hand out of the way. I know, we're all doing what we can here. Voltage, of course, using algebra, is equal to your current times your resistance, right? And of course, resistance, you know, this is an equal sign. And of course, if you wanted to just get the resistance, it would be voltage divided by current, right? So it's just that way. So let's go back up to the example. And you all remember, all these PowerPoints are up on Canvas. So here where you have 1.5 volts and 20 ohms, right, you would get 0.075 amps, right? Okay? So that's electricity. You're now doing electric circuits. Congratulations. Pretty cool, huh? All right. Yeah, and remember, so if you have a bigger wire, a fatter wire, it makes sense. It's actually like, it's easier for the electrons to flow. Just like if you had water flowing, you could pump a lot more water through a fatter pipe than you could through a little narrow pipe. And so it's kind of like that. A bigger wire, a heavier, and it's called a gauge. A heavier gauge wire, it's easier to flow, right? And then here you want to have a resistance because you want this element to glow so that you get light, right? Okay? All right. Now, yeah, here they're talking about resistance of batteries. We're not going to worry about that. I worked in engineering forever. I never worried about, I mean, there is, batteries themselves have an internal resistance, but we're not going to worry about that. That's a special situation. You don't have to worry about that if you're working on your car or working on fixing toys or a flashlight. You don't have to worry about the internal resistance of the battery. So yeah, and here they're just pointing out the voltage is also called the electromotive force. So if you see the word electromotive force, that's just another term. People use the term voltage as well. So that's okay. So the book kind of uses them a little bit interchangeably. It has a little bit of a different sign. Instead of a V, it just has this little E. I just like to use voltage all the time. When I worked in engineering, we called everything voltage. We didn't say electromotive force. But this is out here. Well, we're not going to worry about it for what we're doing here. So, okay, let's continue. And here they're just giving another example. We're not going to worry about that. I gave you the example you need to know. Okay. Now we're going to talk about what's called series and parallel circuits. So let me go like this for this particular one. And yeah. So this is called a series. Now this is the symbol for a battery. Notice how it has a plus here. There's kind of a bigger line and there's a smaller line here. That's a symbol. You're looking, this is a schematic, right? Congratulations, you're doing schematic. So this is a schematic showing what this here is physically. So now if you had a battery, and this is a rubber band and you've attached wires to the battery, it can go to a switch. Notice you would have the switch here. This handle goes up and down. When you close it, this closes the switch. Now current is going to flow. So, and this is showed schematically here. Here's a schematic. So the current will flow. Remember, we say current flows from plus to minus. So you close this switch, that represents that. Then the light bulb, well, with the resistance, they use a symbol, it's a jaggedy line, okay? So see this little symbol here of the jagged line. Whenever you have a resistance, so if you have a schematic, it's represented. So your voltage, your battery is represented by this diagram, whatever your source of voltage is. A switch uses this sort of a symbol, two circles, and then a little thing that goes up and down. Then whatever your load is, this could be a light bulb, or maybe you're heating something up, or this is what you use to charge your phone, or something like that. But it's a load. It's the battery. All the battery knows is now it has some kind of resistance, and the electrons are going to use, right? So you draw it with resistance. So that's what this symbol is here. That's resistance, okay? So it's called a series circuit, and it just means like everything goes in a line like that. You'll see what I'm saying in a second. It's a single loop. Well, now you can have a thing. So yeah, so this is, now here, if you had 3 light bulbs, you would represent that by 3 of this resistors, because there's 3 loads. This is a load on the circuit, that light bulb would go, that light bulb, right? But what would happen now is the current, the voltage is going to get lower for each one of these, because the voltage has to go through this one. So the current is getting forced through all 3 of these things. It makes it tougher on the battery when you have it this way, because instead of just 1 light bulb, it's got to light 3 light bulbs now, right? So all the light bulbs are going to be a little bit dimmer. That makes sense. So here, so to figure out the resistance, remember in ohms, you would add these. You would add these. It would simply be, so if you say, what is the total resistance? In the previous picture, there was just 1 resistor. Well, you would add these. It would be R1 plus R2 plus R3. So now when you just wanted to do the formula we just figured out, for current is equal voltage divided by resistance. So you would just add all 3 of these resistance, right? Then you could add that, you would get this R, then you could divide that into your voltage and get your current, right? So simple. So if you have more resistors, you just add them all up, and as far as the battery is concerned, it's like there's 1 big resistor there, right? So that's the way it thinks. Yeah, and the same amount of resistance goes through all of these, right? It can't help it. It's just like if you had, right? So the same amount, just like if you had a water pipe, right? That's what they're saying here. The same amount of water. Yeah, so it's going to flow. You can't have it slow down here, then go faster here, right? The same amount of current that leaves is going to come back, right? However, the voltage, you're going to have, the voltage is going to be shared. You're going to have some here, some here, some here. All right, so this is just a little test. We're not going to worry about that. Let's go on. All right, let's move on. So let me go to here. Test. Okay. Take those. All right, now we're going to talk about a parallel circuit. So what do they mean by parallel? Well, it's here. See, it's a slightly different configuration. Now you have a battery, but instead of all of the resistors being in one loop, now you have 3 different loops. Here's a loop here, here's a loop here, here's a loop here. Huh. So why would you do that? Well, now what happens is, now the voltage is the same across all of these, right? So the same voltage that is coming on the previous one, the voltage would go down, and then each one of these would have a lower voltage. Here, the voltage is the same for all of these, okay? But you measured the resistance different. We're going to show you that in a second. So the current is now split up. It's kind of like, that's why they're showing this. If this was a water tank and these were pipes, well, the current is split up now. So you have current going through here, going through here, going through here, right? Or like the water flow. So it's split up. Whereas in the previous one, all the resistors were in the same pipe. Now they're going this way. So it's called parallel. But so how do you do the resistance? This is the important part. Now, instead of just adding all the resistors, now the way you would do it to find out the total resistance, you would do 1 over what would be the total resistance, and it would be 1 over R1 plus 1 over R2 plus 1 over R3. So you just have to remember, the test is going to be open books. You just have to know, this for the test, that to do, when it's a parallel circuit, then the resistance is, it's 1 over. It's 1 over, okay? Yeah, so the voltage now is the same for these. So if this battery was 1.5, then this would be 1.5 volts here, 1.5. In your car, this is the way your car works. See, your car has a battery in your car, and then there's an alternator too that creates current. But then all your devices in your car and your cars work on 12 volts. So this would be 12 volts in a car battery. But then your headlights work on 12 volts, right? And then what we used to call the cigarette lighter, now it's called your 12 volt power source. Now I'm not talking about the USB thing. I'm talking about the other one where you can get power. So that would be 12 volts. Your radio in your car, like you could have a radio here, that would have a resistance that works on 12 volts. So your lights, your headlights and your brake lights, they would work on 12 volts. So everything works on 12 volts, and they each get their individual current depending on their resistance. So if these resistances are different, so your light bulbs are going to have a different resistance than your car radio, it's going to have a different resistance than your electric window that goes up and down, right? But they're all going to work on 12 volts. So this is the way, say, your car is wired. So all these different devices all get the same voltage. They can just make them for 12 volts, right? Okay? So a portion of the current goes through. Because these resistors can all be different. You know, and they will be different if it's different devices in your car, right? So, and here's just some symbols showing it. In series, you know, your devices, your resistances, you add them up. But if they're split up in parallel, then you have to calculate the resistance this way. And then of course, to find out your final resistance, well, you have to take the inverse of that, right? So do the math. Yeah, so here we're going to do, we'll go over this problem. So you have a 6-volt battery, right? There's all kinds of different batteries you can buy depending what you're doing. So here you have a 6-volt battery, and you have 2 light bulbs in series. Sometimes it's kind of hard to look at these wires, especially if you're not practiced, but it's easy to look at the diagram, the schematic diagram. So here they have the 6-volt battery, right? Yeah, this is another symbol for batteries. You can have a couple lines there, right? So there's like 4 lines. So this is showing a battery. And then you have 1 light bulb and another light bulb. So how would you figure out the entire resistance, right? Okay? You do the math. And then E, remember, they can use a symbol E or voltage, right? So 6 volts divided by 5 ohms, and this is the equation we learned when we first started this, okay? So there's 2 different ways to calculate resistance. I'll leave it to you to look at that math, right? Because I want you to practice a bit, so. All right, so let's. All right, let's get through these. Okay. Yeah, now how do you measure? You know, those of you that are in automotive, you're going to have to measure voltages across things. So you'll have a meter, a voltmeter. It'll be a little gauge. It'll either be, most of them are digital now. Back in my day, right, we had a little thing that would go and tell you what your voltage was. And so if you had a battery, and then say if you wanted to measure, are you getting the proper voltage coming out of the battery? Well, you just measure it across, right? And say you know, so the battery is connected to your headlights, whatever. Well, you would have your voltmeter and you just measure it across. Now this has a really high resistance, so really high. So it doesn't affect the current, right? In theory, it doesn't affect it. You can put these probes across your battery and it's not going to affect, and you'll be able to measure. Because say if it was a 12-volt battery, you want to make sure you're getting 12 volts out. If your battery is dying, maybe you're only getting 10 volts out. Well, it's not going to work anymore, right? So you just measure across the battery, right? Okay, let's get through these problems. Now for current flows through the wire, so it's called an ammeter, right? Ammeter, because you're measuring the amperage. That's how much current. That it would be in series. Now this would have a low resistance, right? And so you measure the current going through. Now a lot of you folks that are in automotive, there's actually a clamp on where you don't. What happens is when you have wires, now although there's 2 kinds of ammeters. One, you would have it right in the circuit and it would permanently be there and it would always measure your, but if you're just checking current, typically what there is there's a device where it doesn't actually break the circuit. It's a device that it goes around the wire. When electricity flows, there's a field. There's a field that happens, and you can measure the current without breaking the wire. Because there's actually, when current flows, there's a field that goes through. Felix, what's a field? Well, the gravity is a field, right? Right now, if I let go of this, the gravitational field has pulled this pen down towards my hand, right? Well, there's a lot of fields when you have a charge. You know, the reason why if you rub a balloon on your hair in the wintertime when it's dry, you know, for those of you that have long hair, you can see your hair separating. Well, wow, that's magic. Well, that's the electric charge. There's a field that pushes away, or a magnetic field. If you try to push two magnets and you have the same poles, like a positive and a positive, you can feel the resistance, or the other way, the magnets will stick together. You can feel the force pulling. That's a field. There's just these fields that exist in our physical world. So when electricity flows, you have a field. That's how they can make magnets. So you're able to measure a current. You can either put a device where you're measuring the actual electrons going through, or you can just have a device that wraps around the wire, and that field that is caused by the electrons going through, there's a device that can tell you what the current is. And this is what they use typically in industry and automotive. You wrap it around the wire you're concerned with. You can measure the current because of the field. It sounds kind of spooky and eerie, but we're used to gravity. Well, there's other fields too. There's fields from magnetism. There's fields from electric charges, right? When electrons flow, there's a field. So it's just another field. Just the way the world is. All right, where are we? So I'm going to do these ones here. Okay, we don't need to look at that. We do want to do power. Okay, so we're going to talk about power. Let's talk about power. So if you have current going through a resistance, and say this resistance is a light bulb, and say that light bulb is a certain amount of wattage. Well, watts is power, right? We're used to, inside your refrigerator, there's like a 15-watt light bulb, and the old-fashioned 100-watt light bulbs, right, to kind of get warm. There's wattage. Well, wattage is a power. It's how much energy you're using over time. How do you figure out power? Well, it's easy. Let's go back down here. Power is just equal to voltage times current. That gives you your power. Now remember that voltage is equal to IR. We can see that right here. This is left over from previously. So power, so you can say that voltage is equal to IR, that's voltage, times your current. Well, that's the same as you'll see this sometimes, I squared R. That's where that comes from. So they'll call it your I squared R losses. So another way, if you know what your resistance is in a circuit, and you know what the current is, another way to do it is you can just square the current times the resistance. That's also going to give you your power. Okay? So another little equation. That's how you figure out power. Yeah, power we use all the time. Light bulbs, iron power. When you want to know how strong, when you go to buy light bulbs, they're going to say, well, this is a 60-watt light bulb. This is a 100-watt light bulb. Your light bulbs are rated in power. You buy them based on the power that they output. So power is important. So there you go. Okay, let me look at page 2. Okay. Yeah, the book has some good examples here. If you look at page, here I'm on page 268, 269, it has some really good diagrams. So make sure you read the book, right? You can't just watch my thing once and you know everything. You have to practice with this. So it has a good diagram of what a series would be. Here you would have a light bulb, right? You have a switch. If you had 3 light bulbs, it would be this way. So page 269, or 268, and here you have a really good diagram in your book as well, right? All this is in the book. It shows the parallel circuits, right? It shows how you calculate your resistance in a series circuit, right? I'll leave the math to you. Then on page 270, how you would calculate the resistance in a parallel circuit. Then, this is a really good example. So I want everyone to go through this example. I'm going to leave this to you, right? You all know math well enough. This is right in front of you. So this is page 270, example box 13.2, right? Resistance and current of light bulbs in parallel. So they even show you a nice little picture down here. Okay, and then it's our little formula. And then how do you get the final, right? Well, I'll go through it quickly. So they're saying that these resistances are 10 ohms apiece, right? So it's 1 over 10 plus 1 over 10. Well, 1 over 10 plus 1 over 10 is 2 over 10. But that's equal to 1 over your total, right? Well then, to get your resistance completely, well, you just do the inverse. 10 over 2 is 5. It's as simple as that. Then to figure out your current, well, you know it's a 6-volt battery. It tells you that. Divided by 5, 1.2. Okay? And make sure you do part B as well. So the math here isn't too challenging. The concepts are new, right? A lot of you we haven't done this before. Make sure you go through the book. So page 270 is very important. Example 13.2 is very important. Shows you how to do it. Right? You're a little bit sketchy on how you take the inverse. Well, you do it just like this example, right? It's always going to be the same. Okay? 270. Yeah, 271. These pictures are here again. Measuring a voltage, right? So a voltmeter is a device where you would measure voltage, right? Here you measure it across the battery. No current is going through the voltage meter, but it's measuring the voltage. In order to measure the current, there's two types. One, the current actually goes through the meter. So it's measuring those little electrons going through it, right? The other one that the book isn't showing, but I'm telling you about it. The other one that the book isn't showing, I'm telling you about it. There's a type of meter where you don't actually, all you can do is it just wraps around the wire, and then the field that is produced by the electrons going through, you can measure the current that way. That's the more typical when you're troubleshooting, or your mechanic, when he's trying to fix your car, there's an electrical problem. That's what he would use. It's a field. Whenever electricity flows, there's a magnetic field. There's fields, right? There's electric fields, magnetic fields. They all go hand in hand. We're used to the gravitational field, right? There's other fields. Magnetic fields, electric fields, right? There's other fields once you get into the nuclear world, right? So, okay. We talked about power. All right, so let's go on. All right. Now let's talk about